I'm Dmytro, and I guess Kevin asked me to do a presentation about smart telescopes. I'll do maybe 5 minutes about it, and then if you guys want to discuss any of it, we can chat online on Groups.io or Slack. So just a 30-second introduction, like these kind of pictures. I don't know, is there a next slide where I did like a little family portrait of it? Yeah. So I think Kevin a couple of weeks ago posted like what makes CAS great, and I wanted to kind of add to that, and like this kind of family portrait of these introductory telescopes was kind of what makes CAS great, because I joined about a year ago, and I've been part of other astronomy clubs like in Michigan and Colorado, Northern Colorado, Boulder, and I think CAS is way more outgoing, way more active, a lot more outreach events. And one of the events, first event that I went to was Ivy Creek that Boris continues doing. And I was Ivy Creek, and Dave brought his C-Star. That's where I first time saw it. That was kind of a blind spot for me for these smart telescopes. I saw what it was capable of. I immediately had to buy it. And then eventually when S30 came out, I had to buy it. And then Ken Hand, I don't know if he's here, but he is a great collector of smart telescopes. So he donated Dwarf 2 to the club, and he had Dwarf 3 that I borrowed from him. So kind of all of this is a combination of one great society that we have here. So I had all 4 of them for a couple of weeks, and I tried to bring them all to out to one of the events and try to shoot some pictures. But honestly, it's a little bit hard to juggle all of them together. You have to kind of do one at a time, and it's kind of hard to switch if you have one device. Kind of hard to switch between them. But can you go to next slide? I think so. I tried to put a little table up together to compare them. So I compared S50, S30, Dwarf 3, and Dwarf 2. A lot of this information is available online on YouTube. If you want to go search for it, you'll find it. I probably should thank Tom as well, because Tom, I think, originally compared C-Star and Dwarf and posted some statistics about them. I might have copied your homework a little bit. But first thing I posted place is the price, because I think that's the very first question people will ask. And they're all pretty similar price, and Dwarf 2, I don't know if they're going to be selling it anymore. It's probably going to be on the used market, because it's probably at this point it's outdated. But you could see the aperture and the focal length of them. The biggest difference, I guess, is the sensor, and the C-Stars have a 2 megapixel sensor, and Dwarfs have 8 megapixel sensor, and that bigger and nicer sensor, of course, gives you a lot more detail, but the aperture and the focal length of the C-Star zooms in a lot more, and you can also see the field of view. So almost 3 degrees for a Dwarf in one of the dimensions. And I guess weight is the Dwarf is a lot more portable, kind of almost fits in your purse, literally. C-Star is a little bit bigger. But can we go to next slide? So I just threw a little bit more information here. S30 and Dwarfs, they have the secondary wide field camera. It's kind of nice for finding the sun and the moons. If you don't level your scope perfectly, it really helps. You can just kind of go to it and find it easily. But those sensors are kind of local. I don't think they even post what kind of brand it is, because it's probably some kind of low cost, small sensor, only 2 megapixels. So, but it's helpful for what I do. And if you're interested about tripods, for example, include tripods. Dwarf 3 doesn't come with a tripod. You have to purchase it separately. S30 has a little tiny mini desktop laptop, and the S50 has a lot nicer kind of medium-sized carbon fiber tripod. And if you want to swap them back and forth, they have a little different thread, which is not a problem for serious astronomers or photographers because they might have an adapter already. If you don't have any equipment, you might need to be aware of that they're not easily swappable. And then there's probably a picture to compare the two. So this was a, oh, did it?
There's a bunch of them.
Oh, you pulled a bunch of them.
They're all in there.
All right, I thought it was going to be just one. So I wanted to kind of speed through it. But I guess if you go back to dwarf picture, for example, so this is M13. That was our object of the month last month. So this is, for example, what dwarf can do with it. It has a huge 8-megapixel sensor, and you get a lot more wider field of view to grab it. What I didn't like about dwarf, for example, if you want to compare the apps or the pictures it produces, you have to dig around for information. It's not easily available right there on the screen or right. If you're in the app, maybe, but if you uploaded the picture, you have to dig around to find. It doesn't save the file information with the file, which I found very strange for a smart telescope. So you have to go and find the JSON file, which maybe software engineers love because you can do a lot more automation with it. But for lay people, very beginners, they wouldn't even know where to find it or look at it. And after you do a long exposure, you have to do some math to figure out how many minutes you've exposed. So you'll find that it was 15-second exposure. You took 27 shots, so you have to do 27 times 15, and you already kind of got bored. But it was probably 6-7 minute exposure or something. But anyway, if you go to the next shots.
Yeah, so the dwarf is a little more oriented toward the technos.
Right. Well, yeah, so that's what's going to be my final kind of suggestion is that dwarf is oriented to more professionals, maybe a steeper learning curve, and C-star right out of the box for complete noobs. It's kind of perfect. Yeah. So this is same object taken with C-star S50. There's a lot smaller resolution, but to me, it's more satisfying to even kind of, after 10 minutes or whatever, that exposure is 12 minutes.
12 minutes.
And it has this overlay, which is, again, probably serious astronomers don't care about overlays. They want to maybe even hide all of that. But to a person like me, I want to immediately see what the object was, what the exposure was. So I kind of love it for that. And I don't have to dig around to find any more information. You can slide to the slide next. Oh yeah, so this is side-by-side comparison. So this is
scale's about the same.
Right. So one thing super amateurs like to ask, well, you have a telescope, how much does it magnify? Well, this is a smart telescope, it doesn't have an eyepiece. So to even approximate what the magnification is, you can do some magic math of sensor area and divide by focal length by the sensor area maybe. So it's probably 30-some times magnified. You can check my math later and we can debate it online, but you can do your own research. But so magnification is about the same, maybe S50 a little bit more magnified. So, but it's also interesting to see how the sensor is oriented inside the telescope. So by default, when you point dwarf, it's oriented this way, and the C-star is kind of vertical, like a cell phone selfie kind of thing. But so you can also see the 2 megapixels versus 8 megapixels. You can fit four of those in one frame. So it's kind of pros and cons of two telescopes right there in one shot. So I don't know, do we have any more pictures here? Yeah, so this is one I posted on Slack some weeks ago. So that was my first attempt to compare them. So this was very kind of my very first time using dwarf, so don't judge it by the quality. And also when you try to switch between scope and scope, you kind of forget which buttons to push and where to do denoising and stuff like that. So I'm sure Dwarf 3 and Dwarf 2 can do very nice pictures if you spend some time learning how it works. But again, by default, for noobs, I thought C-stars was very good. And one thing I guess I can mention, because we do a lot of outreach, is that I think C-Star is a lot more better for public presentations, because you can kind of pull it up within a couple seconds. You already have a picture on the screen. You can show it to people. When you switch to the next object, it's very fast to switch. With dwarf, there is a lot more clicking around, post-processing. If you want to do denoising, it might take 5 minutes, maybe more. So if you have a crowd around you, you don't want to tell them like, well, wait 5 minutes for this denoising to finish. So it's probably a lot better for kind of on your own astrophotography. And I assume 8 megapixels is what takes long. Maybe if you do 8 million divisions or multiplications or whatever it does, it's probably what takes long. Yeah, so if we want to speed through the rest of the slides, so this is way too fast. So again, a little bit of a comparison of the field of view and how much it magnifies. So kind of, I think all of these I try to keep on the same pixel scale kind of thing. So you can see Dwarf 3 and C-Star are almost similar. And then with a smaller lens and smaller focal length of the other scopes, you get a little smaller photo. So if you're primarily want to look at the moon, for example, so moon will look similar in size. Moon looks very pretty in the S50. I don't know if I added, I didn't get enough comparison shots yet, but I might do a similar presentation, maybe one of the Saturday learning sessions. If there's enough interest, I can put something together with more detail. So can you go one more shot? So this is an example of dwarf doing wide field astrophotography. And I think out of all those 4 scopes, only dwarf 3 is able to do it right now. I don't know if S30 might get updated, but I didn't find that option to do it there. And I guess that's an example of how long it takes to then denoise. I think it's North American nebula. So, and also like the interface of all these apps, it kind of looks like a smartphone on a camera. And if they ask me, I would probably redesign a lot of this, because it's a lot of features are hidden way into menus and submenus, and then you get a little chunk of area to actually pick something out of it. But is there anything else left in there in the presentation? Oh yeah, so
Yeah.
yeah, so this is kind of my summary. So I think C-Star is a lot more intuitive, and also when it's stacking, it kind of adds a lot of unnecessary airplanes and satellites into the picture. Dwarf rejects those, but it saves the frame rejected frames. So that's again like a little pro feature versus amateur feature. That doesn't save, C-Star doesn't save rejected frames, and Dwarf seems to save it. And there's a lot more features in Dwarf that you can play around with. And I think if you wanted to look at planets like Saturn, Jupiter, I don't think neither of the scopes are good at it. You could, I mean, Dave looked at Pluto, so Pluto is great to find it in the sky. And but that's and I looked at we found asteroid Vesta that was presented a couple meetings ago.
Okay.
But anyway, I think that's it for now. If you guys want to know more, we can probably chat online about it.
That's cool.
You want to do the spiel?
Yeah, sure. So next month in August, we have Dr. Cosima Ivansteiner. She's going to be here. She's got a presentation on observing nearby galaxies. She mentions in here a bunch of stuff, but they're looking at stellar nurseries and the like. So she'll be here on site, and so we're looking forward to that. And on the next slide. So tonight's speaker online, by the way, he's going to be online, is Dr. Marshall Faintich. Dr. Faintich, he's been with the club for about a year, I guess, maybe about a year. And I talked to him early on because the guy's got an incredible background. He's you know, pretty versed in many things. So I said to him, hey, would you give a presentation on your background, your career, how all those things you did, starting with astronomy and how that got you to where you are today? And he said, yeah, he'd be happy to do it. So with that in mind, can we get
Oh yeah, we can get them up.
Got it on?
We have a.
Can you see it?
Let me stop sharing this, and I'll drag Marshall over here. okay. How does that look? Do we like how that, let's pin him.
Yeah, it's shared for people.
Yep. All right.
Okay, can you all hear me?
Yes.
I want to thank Kevin for asking me. I was a little bit reluctant to talk about my career, but I thought if I made it in terms of the critical events and the people I met along the way, you might find it of interest. I would appreciate, though, if you wait till the end before you start asking questions, because I would like to get through this. As a little kid, I did all the same things that everybody else did, but I was also very interested in the moon. There was times when I'd get up in the middle of the night when I should have been sleeping, just staring at the moon. And when I was 10 years old, something happened. Sputnik got launched. And I said to myself, I want to do that. I had no idea how I would, but I wanted to do that. And that's how I started my career. In the summer of '63, my 16th birthday, I had $10 birthday money, and somebody was selling a used Edmund Scientific 3-inch reflector, terrible telescope, mostly cardboard, with a rickety mount tripod. And I took it outside. I thought I could see Saturn. I had a little star chart. I looked in the eyepiece and I saw nothing. I looked at my star chart again. And when I went back to the eyepiece, I actually bumped the telescope and moved everything. And then when I looked in the eyepiece, I was lucky and I got hooked. A year later, I graduated from high school and went to my second choice, the engineering campus of the University of Missouri. My father gave me $50 and said, good luck. So with the fact that I was putting myself through school, I doubled up on all the courses, averaged 20 hours a semester, and graduated in 3.5 years, and with a BS in applied mathematics. They only had 2 astronomy courses. Both of them were terrible. The basic course was taught by a professor they put out to pasture, and the planetary physics class was not what I thought it would be. It was the professor's research on what does extraterrestrial life look like. And it started off okay. He said if there were human-like figures on a planet around a red star, their eyes would have to be further apart to see stereo with the longer wavelengths. But then it went downhill from there. So I started my graduate school at the age of 20 at the University of Illinois. That's me at the 12-inch refractor. And my first advisor was the head of the department, George McVitie. He was also a cosmology professor. I'm glad that graduate students got free paper because the semester I took cosmology, I was averaging 100 sheets of paper a night doing the homework. I show this 2001 Space Odyssey. If you saw the movie, it came out around then. And when they're decommissioning the robotic computer, HAL, and taking it apart, at the end it says I was born in Urbana, Illinois. And everybody thought that's because Illinois was building the largest supercomputer. But about 10 years later, I read an interview with Arthur C. Clarke, the author, and McVitie had been his mentor in England. And that's why he said Urbana, Illinois, he was honoring McVitie. Well, my first semester, I was on an NSF traineeship. I got very interested in astrophotography. This is a modern photo of the telescope with my second astrophoto. It was Saturn. Astronomers use glass plates to prevent shrinkage, and they were red sensitive. So we had to load the glass plates into the plate holder in total darkness. Unfortunately, the plates came in 8 by 10 inch size, and the plate holes were 2 by 3 inches. So we had to cut them in total darkness. And then to know which side was up, we had to put that freshly cut glass to our tongue to taste the sweetness of the emulsion. The dome had a big metal chain to close it, and it had to be cinched it really well. I was there one night. I thought I had cinched it pretty well. Big storm during the night, and one in the next morning, and the professors were shoveling a foot of snow out of the dome. And I thought my career was over right there. And also the graduate students' offices were in the basement, and the stairway around the pier went around in a circular area. And once a year, 3 years in a row, I have forgotten that the last step was right at this doorway, and I'm 6'1", and it was only 5.5 feet, and I cracked my head 3 years in a row. One of my office mates was a graduating PhD. Knowing I wanted to get in the space program, he said, pick a subject matter area where when you're done, you know you're done. Once a month, we had what was called the Graduate Student Journal Club. And normally it was a grad student giving a talk on a recent article he had written, but every once in a while we had a guest speaker. And my first or second meeting was Kip Thorne from Caltech. He later won a Nobel Prize. And if you saw the movie Interstellar, he was the technical advisor for that movie. But pulsars were brand new, and astronomers called them little green men. Time magazine called them pulsars, and that stuck. But Kip Thorne gave an hour lecture showing beyond a shadow of a doubt that these were rapidly expanding and contracting white dwarf stars. 6 months later, one more observation, and it was proven that they were rapidly rotating neutron stars, which was a very valuable lesson because it said all you need is one more observation and everything can change. And speaking of Nobel Prize winners, a couple of years later, McVitie had retired, and John Bardeen, double Nobel Prize winner, was on the selection committee. Excuse me. Iko Iben from MIT was applying. Bardeen walks in. There happened to be a empty seat next to me, and Bardeen walks over to sit down next to me, and I was hoping to talk with him, but all I could do was say hello, and he said hello back, because as soon as he sat down, Iko Iben started talking, and at 5 o'clock, Bardeen looks at his watch, gets up, walks out, and Iko Iben closes the notebook and sits down. He wasn't there to lecture to the grad students. He was there just to audition for Bardeen, and he did get the job. The other thing I learned my first semester in graduate school was about Le Gentil, the French astronomer, and I'm going to give you the very short version. He wanted to measure the time it took Venus to transit the sun. This transits take place 8 years apart, and there's more than a 120-year cycle between them. He set sail for Pondicherry, India in 1761, couldn't land because there was a battle going on in the harbor. And rather than going back to France, he decided to take more astronomical measurements over the next 8 years. He went to Philippines. He was going to view the transit from the Philippines. He decided to go back to Pondicherry. It was clear in the Philippines. And when he got to Pondicherry, as he had written, it was clear for 2 months prior to the transit. A few hours before the transit, a storm blew up. He missed the entire transit after waiting 8 years. And right after the transit was over, the skies opened up again. But that's not all, because on the way back, they lost most of his notes. He got dysentery, almost died. And having been gone for more than 8 years, the French thought that he had died and gave his entire estate to his nephew, who gambled it away. And Le Gentil died penniless. So the two life lessons were, if you find a good observing spot, stay there. And if you miss a bad event or miss an event that you really want to see, think of Le Gentil. It could always be worse. So 45 years after that, I realized that the next transit in 2012 was going to be on my 65th birthday. I had forgotten about the one in 2004. Of course, it was cloudy, so I missed it. But then again, I thought of Le Gentil, and I did not worry about it too much. So the next, in 68, I got into an NSF fellowship. I chose celestial mechanics as my area of specialty. Lane Abner was my advisor, and I did my master's thesis on the restricted four-body problem. In a year, finished my master's, then another year finished coursework for prelims. If you have to excuse me, I keep getting a drink because I'm not feeling real well. The restricted three-body problem involves two major masses and a small infinitesimal mass. And there are 5 Lagrangian points. L1, 2, and 3 are unstable, but L4 and L5 are stable. And if you look at Jupiter and the sun, there are the Trojan asteroids that go around the orbit with Jupiter. Now, in those days, there was a whole group of people who wanted to send a space station between the Earth and the moon at the L5 point. It's called the L5 Society. But that really didn't work very well because the sun has a much stronger gravitational pull on the moon and the sun than they do, moon and the Earth than they do on each other. So it was really a four-body problem. So what I did for my master's thesis, I developed the equations of motion, the model for the restricted four-body problem. Here's one example a few years later. And think of this as the gravitational field. And there are 6 unstable points and 4 stable points. And if you roll a marble around like in a roulette wheel, if it stops in one of the stable points, like in the center, it'll stay there. But if it's in one of the saddle points, it will stay there momentarily and fall off. So that was a really interesting thing to be able to work with. And I started using that in my doctoral thesis. So when I was ready to take my written and oral prelims, we were responsible for every course taught in the astronomy and the minor departments and every lecture presented while we were there. I ended up buying all the astronomy books for the courses I hadn't taken and learned them on my own. For my math and physics, I only studied one area. I'll talk about that in a minute. Most of the grad students spent 6 months to a year studying. I decided to do it in 6 weeks. I studied every day, 7 days a week, from 6 in the morning till midnight. And the week of written prelims, I woke up every morning at 4 o'clock asking myself questions in the middle of in my sleep. The year before, one of the grad students was so stressed, he was driving his car. He ended up in the middle of a cornfield, had no idea how he got in there, didn't know where he was. He had to ask one of the farmers how to get home. So if you pass the written exam and we didn't know, then the oral exam was a way to make it up. So I'm waiting to take my oral exams. The doors cracked open, and I hear McVitie say, "This champ got the lowest score ever on written exams." And I thought he was talking about me, but he actually wasn't. So I was really nervous. So I went into the exam, and the physics guy, the physics professor, says, "Okay, well, this is astronomy. Would you describe how a star image is formed in a telescope?" Well, that's the one thing I had studied, the diffraction pattern of light going through a circular aperture. And after writing 4 blackboards of Bessel equations, I turned around and said, "Any other questions?" And he said, "No, that's enough." But then McVitie asked me a question I never prepared for. He said, I know you're interested in astrophotography. If I set a telescope, a film camera up on the moon and pointed it at empty deep space and left the shutter open, would it fog the film? Well, that certainly wasn't in any of the books. So I thought for a few moments, and I said, well, you know, the temperature of deep space is 3 degrees Kelvin. And the black body curve for 3 degrees never quite goes to 0 as the wavelength increases. So yes, there would be a little bit of energy at the same wavelengths as the emulsion of the film. And if you left it open long enough, it would fog the film. And McVitie had a very slight nod to his head, and I knew I'd passed. So in my doctoral thesis, I wanted to look at the perturbations of cometary orbits. Now, at first I had 2 advisors, Avner for social mechanics and Stan Wyatt, who is our solar systems guy. They couldn't agree with each other. So eventually Stan Wyatt became my advisor. Now, if you look at comets, there's a Kuiper belt that is in the range of the solar system. And these comets either were formed there or were captured or there. But I was interested in the Oort cloud. And the comets go halfway to the nearest star. It doesn't matter whether they were formed there initially or they were perturbed there. We know there are thousands and thousands of comets halfway to the nearest star with periods on the order of 10 million years. So when I did my degree, there were 509 long period comets that were known, and the distribution of their perihelia, which is the opposite from where they came from, was not random. And my hypothesis was why? Well, I thought that the perturbations from passing stars caused these comets to change their orbits to come in to our visible range. At first, I developed 2 analytical models. One was an impulse model looking at velocity changes, and the other was a standard variation of orbital parameters. These got preliminary results, but there really wasn't what I wanted to show. So I developed the equations of motion for what I call the restricted hyperbolic 3-body problem. So as a star comes along, it's pulled ever slightly toward the sun and then goes away, and that's in a hyperbola. And I developed numerical models for that, and I ran hundreds of models on the computer at the University of Illinois. I only had very limited computer time, but the computer center was open from midnight to 1 a.m. free to the public. So for more than a year, I'd go to bed at 10, wake up at 11:30, drive the computer center from midnight to 1 a.m., throw card deck runs into the computer, and then pick them up the next day and come back and go to sleep after 1 o'clock in the morning. And this is just one example. If the star's here, this is the unperturbed path of the comet. And you can see that when the star is up in this direction, it pulls the comet toward it, away and down. And then this is the new orbit that it's in. and I ran hundreds and hundreds of examples. And what I found is that in the solar motion coordinate system, where the net effect is stars streaming in this direction, the biggest effect on the perturbations are the mid-latitude zones. Very little in the polar and the equatorial zones. So it's more likely to see a comet coming from the equatorial or the polar zones than the mid-latitude zones. And similarly, because of the net effect of star streaming is this way, more in this hemisphere than in this hemisphere. The same way as we see more meteorites after midnight than before midnight. Well, there's 7 inequalities then that if my hypothesis were true, all 7 should be true, but only 5 were true. But as they say on TV, but wait, 90% of the Earth's population lives north of the equator. And if you look at the cometary observations from -30 to -90 degrees, they're far fewer. So when you adjust the bias for that, all 7 inequalities hold true. So some of the conclusions I found is that if there is a long period comet with about 10 million years, by the time it, or before it makes one full revolution, it'll get perturbed out of the visible range. Wyatt and I did some preliminary research on gas clouds perturbing cometary orbits. And some of these comets will get escape velocity. And if you go out to about 100,000 AU, and 1 AU is the distance from the Earth to the sun, about a quarter of the comets have already been stripped away from the cloud. Now, Wyatt and I wanted to publish this in Icarus, and Carl Sagan was the editor of Icarus at the time, and there were some questions about figures or things that I don't remember how many length of the article, number of figures. And Wyatt called up Carl, and he was supposed to meet me between sessions at an astronomy conference. Most of the professors did not like Carl Sagan. Half thought he commercialized astronomy, and the other half thought that, well, I think they could have done it themselves, so they were unhappy they didn't do it. So I'm talking to Carl. I'm asking him a first question, and in mid-sentence, somebody comes up to him and says, "Carl, the reporters are here." And he turns around and he walks away from me. Never said excuse me, never said he's sorry, never said he'll get back to me. So you know what my opinion was of Carl Sagan. Next critical event, I got my degree in '91, and I wanted to work for NASA designing planetary missions, and the Apollo program ended. The NASA put on a hiring freeze. There are more than 40,000 unemployed aerospace engineers on the West Coast alone. I applied to over 100 companies, no success. And then a recruiter came to campus from the Naval Weapons Lab in Dahlgren, Virginia. He spoke with me for 1 minute, and I told him what I was interested in. He said, "I'll offer you a job." And I said, "I'll take it." 2 weeks later, I get a phone call from McDonnell Douglas Astronautics in Huntington Beach, California. I had not applied to them, and they offered me a job over the phone. And I said, "Well, I'm sorry, I've already accepted a job with Naval Weapons Lab." But a good friend of mine, Mike Colbert, had to leave with his master's degree for financial reasons, and he's looking for a job. He had already applied to 200 companies. So they hired Mike. They sent him to Caltech for his PhD. He went over from McDonnell Douglas to JPL. He became the project scientist for the synthetic radar terrain mapper and the Venus orbiting imaging radar. So that could have been me, but 2 weeks earlier, I did this. So my career went an entirely different path. So I was in the astronautics division at the Naval Weapons Lab, did various satellite system studies. One of the things we worked with was a geoceiver, and it would acquire data from the Navy transit satellites and self-locate. Over time, it was so precise, we could do polar motion studies, we did continental drift studies. 3 of the guys I worked with had worked on the Mark II Aiken relay calculator, and they showed me the moth that had gotten beaten to death by one of the mechanical relays, and that was the first computer bug. Paul Weitz was also, he was the first astronaut that I met with. He was the commander of the first Skylab. And of course, I was still collecting stamp sends, so I brought in a plate block and got Paul to autograph it. One Sunday morning, I went in and do some work in 1972, and I said, you know, if we put clocks on the geoceivers and we broadcast the clock time and the position, we could navigate based on the time it took for the signal to travel, let's say, to an aircraft. And by time difference of arrival, we could navigate fairly precisely. And I worked out all the math for it. It wasn't that complicated. And that led me on two critical event paths. The next morning when I presented to my boss what I had done, he had a big smile on his face. And I didn't know for more than a year why, but he wanted me to present time difference of arrival to the entire technical staff. Excuse me, that summer we built an engineering model and tested it and showed we can navigate by that. And then I raised the question, well, how do we know if we can see all of the geoceivers? And he said, well, there's something going on at Fort Belvoir that maybe you can answer, get an answer to that question. But I'm going to come back to Fort Belvoir. So 5 months later, I go back to Dahlgren, and they had gotten me a high-level clearance, and I'm on the team with about 4 or 5 people helping design the orbits for something called Timation. This was a Navy satellite navigation design based on time difference of arrival. And because that was classified, that's why he couldn't tell me why he was so happy that I figured it out. Some of the studies I did was generate computer views of what face of the satellite would see the sun to compute the solar panel power as it went around the orbit. But my primary role was to decide what is the optimal altitude for the configuration of satellites. The lower it is, the better the navigational accuracy, but the more drag, the more chance of being hit by terrain, and the more possibility of enemy attack. The higher it is, you eliminate that, but you lose accuracy. So my job was to determine how high could I make them when there's a full constellation of satellites and still meet the navigational accuracy everywhere in the world. Now it's interesting, the Air Force had a project called 621B. They were trying to build a similar system. I think their orbits were pretty poor, but their satellite was okay. And the Department of Defense did not want to build two systems. So they took the Air Force's 621B satellite and the orbits that I had worked on and made one system. And they called it Navstar Global Positioning System. And we know it now as GPS. And when we worked on it, there was absolutely no thought there would ever be a civilian application for it. Okay, so let's go back to Fort Belvoir. Remember, I was trying to figure out why or how we could see the various geoceivers. Well, they had just gotten a Dicomet system. It can scan a little slide. You take the scan slide to a 9-track tape, process it on the mainframe computer, bring it back, print it out on or display it on a small circular black and white CRT tube, and a Polaroid camera took the picture. That system in 1973 cost $1 million. The Army had just built the first digital terrain database, so I scanned the image for that, and I wrote software to generate a perspective view, laying imagery over the terrain. The entire computer complex had 240K, not megabytes or gigabytes, but kilobytes. And it was taking me hours and hours to generate a single scene. So I talked to the computer staff and they said, okay, normal programmers only got to use 64K. They would give me 235K because I needed 5K to keep the computer building running, the computer system running. So this is the first example of anybody ever overlaying terrain on imagery on terrain and doing a perspective view, 1973. Well, at the end of that assignment, some folks from the Defense Mapping Agency in St. Louis and the Aerospace Center, Defense Mapping Headquarters and the Aerospace Center in St. Louis said, can you simulate radar? And I said, I don't know, give me somebody who knows radar, we'll see what we can do. But I'm going back to Dahlgren for at least a year. So a year later, I ended up in St. Louis. By 1976, we had got another Dicomet system, and now it was $76,000 or $70,000. 3 years later, we had it written in microcode from my mainframe software, and that ended up on Walter Cronkite's TV show, The Universe, showing the future of digital cartography. And this shows one of the simulated radar image versus the actual. So it worked pretty well, let's put it that way. The two guys that were working with me and I decided to start messing around with other kinds of imagery. This was, again, in the beginning of digital imagery. We got some Landsat imagery. We wrote and designed some median filters to get rid of the pixel dropouts. And then we wrote some histogramic enhancement routines to make this image look like that. And I was briefing on the average of 100 people a week from all over the world for 2 years. A lot of folks said, we don't believe what's in this image came out of that because they didn't understand it because it was all so new. One of the guys I briefed was Ray Arvinson from Washington University. He was on the Viking orbiter team. He gave us some images that looked like this. And when we processed them, it looked like this. Every image had one of these donuts in it. And we went back to Ray and I said, well, what's that? Well, he didn't know. So he went back to the orbiting team and they concluded that this was a diffraction pattern around the spotted dust in the camera, on the Viking orbiter imagery camera. Ray went on to be the principal scientist for the first Mars rover. And for a couple of years, I served on his advisory board for selecting Mars and Venus imaging sites. Well, with all this notoriety, with all these people I met, I spent a couple of months working at the French Mapping Agency in Paris. By 81, I was the chief of advanced technology. And while at DMA and afterwards, I worked with members of the White House staff, members of Congress, cabinet members, military leaders. I was the DMA rep to international organizations, both the cartographic and remote sensing societies. I was the national director of the American Cartographic Association for a couple of years. And with the simulator work, I was involved with both the commercial and the military imaging societies, or simulator societies. From 87 to 97, I co-founded a company in St. Louis called Trifid. You all may pronounce it as Trifid. The movie The Day of the Trifids was fairly new, or was out then and popular, so we wanted everybody to remember our name. So even though it was one F, we still call it Trifid. And the image I show here, we won first place in an international contest. We took one 30-meter resolution Landsat image and one 10-meter panchromatic spot satellite image, used it as a stereo pair to construct the terrain, used the color from the Landsat and the detail from the spot, and generated this perspective view over Palm Springs, California. This was 10 years before Google Earth. So that's what we were doing then. And a lot of people were interested. Obviously, I didn't do Google Earth. I did other things. Now, because of the notoriety I had, a lot of people were contacting me. Jim Irwin was on Apollo 15, and after he got back from the moon, he became very religious, and he started a company called High Flight. And he contacted me and came out to St. Louis twice. He wanted me to help him find Noah's Ark on Mount Ararat in Turkey, and he was trying to raise money. And I told him, Jim, if we see something in satellite imagery that looks like it might be the Ark, I can give you precise coordinates, but I was not going to guarantee it'd be Noah's Ark. And about 6 months after the second time he visited me, he died of a heart attack, and that project went away. So from 97 to 2006, I was in Northern Virginia. I started out at Orb Image, Orbital Imaging Corporation. Our Orview 2 satellite was a raving success, low resolution, but high definition color. The flagship was our Orview 4, $400 million satellite. On launch, there was a problem, a minor problem between first stage and second stage separation. The satellite reached orbital altitude, did not have escape velocity, and $400 million went into the Indian Ocean. So I went looking for jobs other places. In 2006, I moved down to the Charlottesville area, Central Virginia, and I wanted to do consulting work in Northern Virginia, but it turns out, consulting work here, but all the work was in Northern Virginia. I did have one job with the National Radio Astronomy Observatory. It turns out my boss at TASC, who didn't want me to leave, but I told him I'm leaving anyway, he was the graduate school dormitory roommate with the director of the NRAO. So he gave him a call and I had a short contract. But that was the end of my contract, and then I retired. Another critical event, I was still collecting coins in the mid 80s, and I was reading a book on the Anglo-Gallic coins of medieval times and Anglo-Gallic coins. And what that is, those are the French provinces held by the English. And in 1290, the future Edward II, the Crown Prince of England, was named as the Count of the French province of Ponthieu, but that was contested. This is the only coin he struck. And with my astronomy background, I said, God, that looks like an annular eclipse. So for the next 6 months, I wrote on my home PC, it was an IBM Model 20, software to make maps and plot eclipse paths. And sure enough, an annular eclipse crossed right over Pontero the year that coin was struck. Well, that started me on 20 years of independent research of the use of astronomical symbols on ancient and medieval coins as for political propaganda purposes. When Julius Caesar was assassinated, there was a comet in the sky, and the Romans thought that his spirit was taken up to the gods on the comet. So when Octavian declared himself Augustus Caesar, he struck a coin with a comet with the spirit of Julius. The Roman Emperor Julius II worshiped Mars, the god of war, often sacrificed bulls to him. He struck this coin of a bull with a star above the horns and a star above the shoulder. In the first year of his reign, in Taurus, the bull constellation, Venus was on the shoulder, Mars was between the horns. So his coin was a representation of what was in the heavens to show that his right was divine. He had a divine right to be Caesar. This is an interesting one. This is a quote from the Anglo-Saxon Chronicles. The comets were thought to mean changing kingdoms. There was a bright comet in 1066, which was probably Halley's, and it was the omen for William the Conqueror defeating Harold II at the Battle of Hastings. And in fact, after William succeeded and took over, his wife and her ladies in waiting made the famous Tapestry of Bayeux. And you can see people pointing to the comet, and then beneath it is Harold dying. In the mid-11th century, this coin was struck in the province of France. And you can see the design looks just like was on the tapestry, but there's an annulet above and below. And in my research, I found that annulets were sometimes representing planets, but I didn't have access to the tools I have today. So in putting this presentation together, I put this into Stellarium and Halley's Comet, and sure enough, it was between Saturn and Jupiter. So that's Saturn and Jupiter on the coin. The last example that I want to show is there was civil war in England between 1135 and 1154, and a total solar eclipse crossed England. Now, the civil war was between Stephen claiming the throne and the Empress Matilda, who was Henry I's daughter. And one of her loyal supporters said that the eclipse was going to be for sure a sign that she would ascend to the throne in Stephen's downfall. So he went ahead and issued a coin. Numismatists call them mullets, but it's a star with a hole in the center. And when I look at that, I see a total solar eclipse. Well, I did thousands and thousands of examples, and that accumulated in 2008 when McFarland published my book. Okay, let's end up looking some astrophotography. I bought a C8 when I was in St. Louis. I did planetary photography. I actually postponed cataract surgery by 2 weeks so I could photograph Hyakutake. And in '87, I went to Hawaii, and I computed that around between 2 and 4 in the morning, I could see the False Cross, the Southern Cross, Eta Carina, and Omega Centauri about 10 degrees above the ocean. So I went out in the middle of the night with my tripod and my 50mm lens, no star trackers. And as I'm crossing the hotel grounds, the automatic sprinklers went on. And I held that tripod high above my head. I got soaked, the camera stayed dried, and I got the photo. So we talked about Le Gentil. This was my first major Le Gentil event. I was photographing the total lunar eclipse in 1989. A bunch of neighborhood kids were there. Totality was 45 minutes. And I had my camera on the C8, and one of the neighborhood kids says, "Mr. Faintich, can I look at the moon through the telescope?" And I said, "Sure." So I took a couple of minutes, got the camera off, put the eyepiece on in the diagonal, focused it for him. And when he was looking at it, I looked up and I said, "Oh no." There was a plane, the same angular diameter as the moon, directly below it. And I knew I had about 2 or 3 seconds, and all I could do was watch. And that's what I saw, but no photo. But I did get lucky a few years ago and got this from Crozet.
Nice.
And one more Le Gentil event. I took my first family for a week to Hawaii for this 91 eclipse. 90% chance of sunshine. On July the 6th, I got this photo of the 4 planets in a line. And then we went to the Big Island. And the hotels were along here. the two volcanoes were always covered in clouds, and everybody was going to look between the volcanoes. It was a 7 o'clock eclipse, or 10 after 7. I went out the day before with my family, and we found this spot. There's a lot of black lava, and people would put white rocks on it with their initials or words. I said, we're going to stop here. Next morning, we wake up at 5:30 in the morning. It's pouring with rain, just pouring. Or excuse me, woke up at 2:30, it's pouring. And so we got to our spot here at 5:30, it's still pouring. And all the tour buses are going further up to between the volcanoes because we were right about here. And I said, we're going to go follow the buses. So we stopped. Sure enough, it starts clearing up. We saw the partial phases. We saw the 360-degree sunset. We saw the shadow of the moon, and then everything was gone. All that moisture had caused mist in the atmosphere, and we could not see totality. 4 minutes later, the partial phases are coming back. People are crying. I had Japanese people coming up to me speaking in Japanese. I had no idea what they were actually saying, but I knew what they were saying, what happened. And you can see what somebody wrote. They weren't very happy. And on the way back, we stopped at the spot where I had picked the day before. Remember Liz Gentile leaving the Philippines? There were a couple of guys there. I said, did you see the eclipse? Yeah, we saw the last 3 minutes of the 4 minutes. And it turns out there was no clouds around the volcanoes that day, and everybody who stayed in the city who didn't care got to see it. Should have stayed at my spot. Okay, so I got really big into doing astrophotography, especially deep sky objects. And I was taking long exposures with, they used to call it ASA instead of ISO, very large grain film. And I thought I was doing great until my next critical event. Hubble got launched. And I said, why am I doing all that work for such terrible results? So I packed up my C8, never used it again. I did do a couple of things, though. I went on a cruise in 1998 to view the eclipse from a ship from Curacao. And this was a 2 o'clock in the afternoon eclipse. And there's 4 or 5 boats out there and in the morning, and it's as cloudy as can be. And all the other boats are leaving. And the captain of our ship said, I'm here all the time. It always is cloudy in the morning. It always clears at noon. No problem. Sure enough, we saw it. All the boats that went out to sea, they missed the eclipse. I went to St. Louis in 2017 and to do the total solar eclipse. And when my wife and I moved to Crozet in 2016, I wasn't doing astronomy really anymore. And I sold my C8 for $200. And I still kick myself for that. But in the end of 2006, I started doing wildlife photography. I've taken over 900,000 wildlife photos, and I have very high-end camera bodies and lenses. And in 2020, I said, I wonder what I can do with those lenses. So I bought a small star tracker, and I started using my camera lenses to do astrophotography. And as you can see, I got some results that I'm pretty happy with. In 2023, I bought a 102 millimeter Mac for planetary work. It's really not designed for deep sky photography. I was able to get a good image of Orion only because it's so bright, but really it wasn't designed for that. But I also use my mapping and cartography and image processing skills to create large area mosaics of the photos I had done. And this is a North American nebula. So this is quite a big range of the sky that was from multiple photos. Now, a new thing happened at the beginning of this year. Thanks to the CAS, I got introduced to the Mark Slade Remote Observatory run by the Rappahannock Astronomy Club. And they've allowed me to have access to their telescopes. I'm currently not operating them on my own. I'm putting in requests for subs for me to process. So I'm still doing my own astrophotography with my equipment. I'm taking some of their subs and merging it with my existing images. And then I've got a whole class of deep sky objects that I can never reach with my own equipment. And the guys there, Myra Masuda and Pete Lakey, I have so much thanks to them for helping me get these subs. And I'm going to be able to continue doing astrophotography for years to come because I've got access to their scopes. So in conclusion, I'd like to leave you with my philosophy of life about my journey. When I was a freshman in college as a math major, and I ended up going to my second choice, not my first choice for school, I said, you know, in real life, the shortest distance between 2 points is never a straight line. So you might as well enjoy the journey. And I've tried to do that. Please visit my website, www.faintich.net. I've got thousands of photos. And now if there's any questions, I'd be happy to take them. Okay, can you hear me?
Questions, questions, questions? Anybody? Well, I have one.
Yes.
What are your current projects? What are you working on right now?
What are my current what?
Current projects. What are you
Well, I'm still going to do more planetary photography, but I really want to go after a lot of the distant galaxies. And I'm doing some work with folks at the Mark Slade. We actually found with one of their scopes, they found a large area as I guess it was 500 millimeter at the time. And I found a distance point, and when I enlarged it, it looked like it's three small galaxies interacting. So we're waiting until next year where we can image that with a 10-inch scope and see if we can discern if it's actually 3 different galaxies. But I'm just interested in everything. I want to try to do the transits of Titan if I can. I've got the the Astronomy Club's C8 that I'm using. My wife and I will probably be moving to senior living in a couple of years, and I'll have to return a bunch of scopes. So I'm trying to figure out what I can use when we do move. And that's one of the reasons why I'm so happy about learning about the Mark Slade Remote Observatory, because no matter what kind of equipment I have, I will always have access to that. But really, if it's in the sky, I've got interest to it. Comets, planets. I've been taking pictures of aurora. I got an interesting photo last year when the auroras were big and very bright. I've got bright aurora with 2 Perseid meteors and Andromeda galaxy all in the same image. So if it's in the sky, I want to photograph.
Questions. So I have one for you. You showed a picture early on where you had the Oort cloud, and
Yes.
it's not clear to me. Is the Oort cloud a ball or is it a saucer?
No, it's a sphere.
It's a sphere. Okay, it is a sphere. Yeah.
Yeah, all different directions. And I've had discussions with Boris, because the question is, did the comets form out there, or did they form in the solar system? And with all the analyses I did, I showed it doesn't matter, because there's been enough perturbations over the age of the solar system that even if they were formed in the solar system, thousands or tens of millions of them would have been perturbed out to those distances. So it doesn't matter where they were formed, they are there. And that's where the long period comets come from.
All right. Any other questions?
Yeah,
Hey, Marshall, thanks.
No, I got a question real quick, Kevin, if I could. It was more of a comment. I really enjoyed, Marshall, your talk tonight, but particularly was laughing hysterically when you said how you tell the emulsion side from your plates.
Yes.
By licking them. I mean,
Well,
that's dedication.
Yeah, it's freshly cut glass, and you got to do everything because it's red light sensitive. Astronomers use glass because film warps and shrinks over time, and the glass is more stable. And it's red light sensitive because in those days, there was a lot of energy, obviously, in the hydrogen alpha range. And so you couldn't use a yellow safe light or a red safe light. So everything's got to be cut in total darkness. And again, the plate holder was 2x3 and the plates were 8x10. So we had a small glass cutter and it was preset for 2x3 with guide rails on it. And so we'd cut it in the total darkness, but then we had to load it properly. And if you loaded it with the emulsion side down, you'd get an out of focus image.
Right.
So the emulsion was very sweet tasting. And we take that freshly cut piece of glass and put it on our tongue. And if it tasted sweet, we knew which side it was.
And you were hoping that there were no glass shards anywhere
Yes,
nearby.
yes.
All right. Thanks.
So that's how I got started doing astrophotography in 1968.
Any other questions?